Swayam Prabha. Digital India. Educated India.
Okay, so today let us wind up our discussion on renewal theory, whatever we started in the last class. So, in the last class we talked about this elementary reward theorem, what we called as ERT. What did this theorem say? If you have a process, so okay, just as a recap, what we did, we started with the DTMC. And we said, okay, let us say start with an initial state I, and I am interested in some particular state J, where S is my state space, and I am interested in my DTMC going back to this particular state again and again. And then we have this sequence of random numbers which we called as lifetimes. Right, and we said that these lifetimes are such that these are all going to be independent. So xn's are independent, and then we said that if you look at xn's for n greater than or equals to 2, they are IID. It is an IID process. Now, if you consider this case, then our ERT theorem, elementary renewal theorem, said that this is under the hypothesis that if probability that xj is equals to is 1 and so what did we say? We said that limit as n tends to infinity m of t by t is equals to, what would you say, this limit goes to 1 by expectation of 2 almost surely, and then we also said that t is also by t. What basically said this result said as is the average number of renewal in the interval in any interval that converges to this rate, which is given by 1 upon expectation of x2. Right, we discussed this last time. If x2 is going to be, the expected value of x2 is going to be large, that means I am not coming back to returning to my state in small number of times, maybe I am going to take large number of rounds to come back. In that case, I do not expect this quantity to be large, right. If this guy is going to be large, this guy is going to be small. This is because this is the average number of renewals in the interval 0t. Okay, fine. How is this theorem? We said we will not go into the proof of this, but let us take it. We understand intuitively, yes, this should be the correct. Now, what is the use of this theorem? Okay. So, if you recall, I had stated an earlier result which we use heavily in the study of DTMC, and that result was about when is a state a j, when if I know that a state j is recurrent, when is it transient, sorry, when it is positive recurrent and when it is null recurrent. So we had stated one theorem related to this, right. So what is that theorem? So in a DTMC, suppose let us say fi j equals to 1 and j is recurrent. Then we said something about this limit, right. What was this? If j is recurrent, we said this quantity we called it something like gamma j, and we said that this guy is greater than 0 if and we said that this is going to be 0 if null recurrent. Actually this theorem is a direct consequence of this elementary renewal theorem. Okay, let us see why this is true. So remember that this theorem, where all we used this theorem in the proof of invariant distributions, right. So when we made a claim that for an irreducible DTMC, it is going to be positive recurrent if and only if pi equals to pi p. In the proof of the theorem we used it, and we have also used it in many theorems. Result. Now why this is true? Okay, so to understand this, now let us come back to our setup here again. One thing we have defined is m of t is equals to what? We have defined it to be m of k such that z of k less than or equals to z, and we call this m of t as what? What? We called it actually renewal process, right, and this is defined for any t. So we have called it as a renewal process. And this is for defined for every t. You give me arbitrary time t, then I am going to tell you how many renewals have happened in the interval 0 t. So what is that m of t is telling? Basically m of is telling how many renewals have happened in the interval 0 to t. Now yes, this t here is continuous time, but so if it is I may also be interested in knowing what happens at some m of n where n is my some integer valued. I can ask this question, right, if this is going to be defined for every possible t that is real, I could as well ask for a particular integer value. So then what is m of n? So that is, in that case I can just write it as indicator that y k is equals to j starting k equals to 110. Is this right? This is basically the number of times I have hit state j till time n, right, till the nth instance. Okay. Yeah, let us assume that for time being all this yn's are such that the n they are of unit. So when I say n equals to 1, n equals to 2 like this, these are like separated by 1 unit. So 1 second, 2 second, like the separation between any two integer corresponds to 1 unit of time. Okay. Now So for this also I can define, I am assuming that I am starting from some initial state y equals to I, right. So I can denote the expected value of this to be k equals to n integer k is given. So Mn is nothing but expectation of this m of n. Earlier we have defined this small m of t, which was the expectation of this m of t, but now I am looking this function only at the integer valued. So it is fine, I can define it in a similar fashion. Now let us look at the average of this quantity m of n by n as n goes to infinity. So as n goes to infinity, what do you expect m of n by n go to? Is it going to be the same limit as this? Or all I am doing is now, instead of looking at t at all possible values, I am only looking at t taking integer values. So if I am going to look at this m of t by t, instead of all possible t's, I only look at some integer values. Is this limit is going to be different from this limit, or it is going to be different limit? It is going to be the same limit, right? So it has to be expectation of x2. Okay, now let us understand what is this quantity. Now let us focus on this. If I have mn by n, this is going to be what? So this quantity here is expectation of 1 by n summation k equals to 1 to n integer y k is equals to j given y not equals to I, right. I am just writing the expression for this. Now what I want, I am interested in knowing the limit of this. So I am just writing this quantity in this. Now limit as n tends to infinity, this expectation. Suppose if I interchange this expectation and limit, what is this quantity is going to be? When I take this expectation inside, then expectation of indicator becomes what? Probability of given y not equals to I, right. So is that same as saying probability of I j superscript k, right. Then you see that you will end up with something very similar to what we have here. Okay, so before that, fine, if I do that, I already see I am going something what I want, but how can I interchange this? When can I interchange expectation and limit here? Can I do that here? So we have been asking this question many times, right? Many times we are facing with this problem of interchanging limit and expectation. Can I do it here? And when I can do it? We know when we can do it. We have seen a couple of cases where we can do it. But the question is this corresponds to one of those cases? So which of these results, like we know, dominance convergence theorem, monotone convergence theorem, bounded convergence theorem, which one we can apply here? Bounded convergence theorem. So if I apply, I should be able to interchange this expectation and limit. So because of that, I could as well write it as things, right. So actually I really don't need to worry about that, right, because the expectation is already inside. So why I need to worry about interchanging them? So I think you guys didn't notice this. So I could directly So anyway, this is a finite summation, right? I really don't need to worry about interchanging that. So I can already always plug in this, and what I get is basically 1 by n p ij of k equals to 1 to n. Why this is I? Because I am conditioned that it is going to start from y naught equals to I. Now we know that this limit is equals to 1 upon expectation of x2. So we now are saying that this gamma j whatever we had earlier is nothing but that was 1 upon expectation of x2. Okay. So now let us look at what is this expectation of x2. What is x2? x2 is the number of time it took to visit my state j for the second time, right? What will be its expected value? So okay, what is this value of x2 can be? What values it takes? x2 takes what values? Integer valued, right? And what is the probability that it takes some value n? 1 by n. Why? So what is the meaning that x2 is equals to n? That means my Markov chain visited return to j again after exactly n rounds, not before that, right? We have used a notation for that. What was that? fjjn, right? We are talking about starting from state j going back to that, and that one, so because of that this guy is going to be fjj of n. Is this correct? The expected value of x2, and this also we have denoted as what? Nu jj, right? And what would we say? When this nu jj is going to be finite, we state this state j to be, are you sure? When vj is finite, is now we say that j is positive recurrent if vjj is less than infinity, and we said that j is null if vjj is infinity. Now let us compare this quantity here. What we are actually showing is this gamma j here is nothing but 1 upon nu jj, right? So is this correct? This gamma j is nothing but 1 upon expectation of x2, that we have shown it to be 1 upon nu jj. Now when the state j is positive recurrent, I know that this nu jj is finite, so this quantity has to be positive. When nu jj is infinity, that is when j is null recurrent, then nu jj is infinity, then this quantity has to be 0, right? So basically what this result we used earlier is nothing but a simple consequence of our elementary renewal theorem. Okay. Now let us further go back one step. So what we are basically saying is the gamma j we have defined is nothing but nu j. If you now recall the theorem we showed for positive recurrence, right? We said that my irreducible DTMC is positive recurrent if and only if pi equals to pi p. And how did we show that such a pi exists? We showed that pi was nothing but this gamma j, right? When we actually showed, we needed to show a pi exists such that pi equals to pi p, and that pi was, we have exactly took that pi to be this gamma j. So our pi j is nothing but the reciprocal of 1 by it is just like 1 upon nu jj, right. So now how to interpret this? This expectation is what? This expectation is about the number of rounds to return to state j, right? This is the expectation on that. Now I am going to return to that state often. That means this expectation is going to be small, right? Then what is this quantity is going to be? Pi j for the corresponding j large. That means I am going to see that more and more, right? So that probability that my Markov chain is visiting that state j is going to happen with high probability. The probability of that is going to be high. That is because the number of times to visit that state again is going to be small. So I will be frequently coming back to that state quickly. Because of that I am going to see that state again and again many times. So the probability that, so also recall that this pi j is the stationary probability that my Markov chain will be in state j, right. So because of that I will, if this guy is going to be too small, I am going to see my Markov chain in that state j for a large fraction of time. That is, the probability of me seeing my Markov chain in state j is going to be high. Okay. Now, so you should be able to bit more comfortable in applying these results, like if you want to interpret, okay, how frequently I am going to visit a particular state and how that is going to be related to his number of mean visits to that time, you should be able to connect all these results and derive any properties, any relevant properties about the Markov chain. Okay, fine. Now let us come back to our renewal process. The way we started defining our renewals process is by taking an underlying discrete time Markov chain, right. We say that, okay, let us yn be a discrete time Markov chain starting in some state I, and now I am interested in visit to particular state j, and for that j I will construct a renewal process. Okay. So when we did like that, the number of visits to number of slots it took to return to the same state j, that was all integer valued, right. But it is not necessary that we have to build a renewal process like this. Renewal process is about anything where you are interested in something happening again and again, right. For example, in the battery case we said that, okay, when the battery life ends, battery life may end at any time, right. It need not be integer valued something. So one could be taking a renewal process as simply something where you have the lifetimes are such that they are identically distributed, and all I am saying is identically distributed. I am not saying this xn's has to be integer valued, they could be possibly continuous valued, okay, such that R and IID. Or more generally I can just take anything. So instead of making this special case, I will just say henceforth for simplicity I can take a sequence of RIID including the first one, okay. So when I talked about my DTMC case, I said okay, I am interested in returning to state j particular j, given that I started in a particular state I. I could as well say why start with I would start with j and then look at returning to that state. In that case I do not need to make a separate distinguish between the first cycle and the subsequent cycle, right. I can, they are all returning to the same state, starting from the same state. So in that case I could just say that these lifetimes are all IID, right. So I will not make a special distinction about the first cycle, all cycles I am going to treat the same including the first one, and in that case I will simply make xn's are IID. Now actually we have already looked at a renewal process where these x1s were exponentially distributed. What was that process we called? What was that called? Poisson, right. We have already looked into a Poisson process where inter-arrival, what we call basically inter-count times are all exponentially distributed, and if this xn's are exponentially distributed with parameter lambda, then actually we had said that this is nothing but a Poisson process with rate lambda, right. So this is nothing but so in this process what we are saying, so how did we describe our Poisson process? Basically we said that Poisson process is a counting process which is basically counting something, and the time between two counts is exponentially distributed with parameter lambda, right. So there count can happen at any time, it is not has to happen at some discrete time slots, right. So in that way Poisson process is actually continuous time process. So for example one case we said that okay, when you guys enter into the class, one guy came, that is the first count happened, after some time second guy came, that is the second count happened, and after some time third guy came, like that. So here you guys are not coming at some discrete times, right, you are coming at some time. So Poisson process is about continuous time process, and now but also it is basically counting something that are discrete, and inter-arrival times there are all exponentially distributed, and this exponential distribution is again continuous random variables. Now the question is, how to define, okay, so now so this is basically Poisson process is also kind of a renewal process in that sense, right. It is basically looking at the counts as something happening again and again, and it is just keeping tracks of how many counts that has happened so far. Now let us define m of t for this. That is number of the counts that has happened in the interval 0 to t. So this is as usual. So no, this is a general thing. This is for any renewal process. So I can also define the same thing for my Poisson process, right? And then it is zk here, which is nothing but x1 plus x2 all the way up to xk being less than or equals to t. I can define this, right, for Poisson process also. So the Poisson process is characterized in terms of this inter-arrival times, and that is going to define my count instances, that is zk's. So once I know that, I already know I can define my renewal process like this. Now what is this basically m of t? M of t is the number of arrivals in the interval 0 t, right. So for a Poisson process, number of arrivals in the interval 0 t, what was that? Poisson, right? And what is the mean of that? 1 by lambda t? Lambda t, right? So what do you expect this to be? What do you expect this to be? Lambda t, right? So this is by connecting. So if I have defined a, and this is a general process I have defined, right? I can define this anything. But if you are going to do this on a Poisson process, you are going to get this. Now, and this is by the argument saying that this is just by the interpretation, okay, m of t is nothing but the number of arrivals or counts in the interval 0 t, and I know that is Poisson distributed with rate lambda t, and that has to have mean bit. But you can also, using this notion that zk is the sum of this, you should be able to again derive the same thing. Okay, you have to check that. Another thing for a Poisson process, let us say these are my lifetimes, right? With respect to this process, lifetime process, I can define a stopping time. That stopping time is m of t. Sorry, I am going to, not stopping time, I am going to define a random time m of t on x. So m of t is what? Basically m of t is always integer valued, right? Even though it is defined for every t, but m of t is giving you integer valued numbers, and this is itself is a random quantity, right? So now I am saying, let us take this sequence and define a random time on that. Okay. Now I want to ask the question, is m of t is a stopping time on this sequence? Is this random time is a stopping time on this sequence x i's or xn's? So suppose if I know that, okay, basically what I know to know, if I want to answer the question is m of t is less than or equals to n, is it enough to know x1, x2, xn? Is this true? So suppose let us say you have been given x1, x2 all the way up to xn. So if you know x1, x2 all the way up to xn, and you have been also given t, okay. If m of t is less than or equals to n, what I know, this sum has to be less than or equals to t, right? But does it also say you that the n plus 1 lifetime has not happened within this within this t? Yeah, but all we know is x1 plus x2 is going to be less than or equals to t. So what is this? Because so this is nothing but if I sum all of them, xi is going to be what is this? This is going to be n, right? This I know as zn, and I know that zn has to be less than, if m of t is less than or equals to n, I know zn has to be less than or equals to t, that we know, zn plus 1, but you do not know anything about, you have been not told at xn plus 1, as this x1 plus 1, if you add to this, that will go beyond t, or it is still going to remain within t? Huh? Maybe or may not be, right? So because of this, without knowing xn plus 1, I can't say that mt is going to be less than or equals to n. Is this clear? That is what we want to answer, whether mt is going to be less than or equals to n. The question is, can we answer this based on this information? Oh sorry, I want to ask this question, right? Whether m of t is equals to n, can I answer this question completely? So it depends, unless I know that the xn plus 1 that is going to happen has to happen after type t, that this sum, if I add xn plus 1 to this sum, that is going to be larger than t, I can't say this, right? So if only if happens that guy, after adding that, if that guy exceeds t, then I know that till n things have been incorporated, n plus 1 is going to stay outside, okay. So because of this, we can't really say that this is going to be m of t is going to be a stopping time with respect to m with my sequence xn, okay. Stopping time. Okay, just a minute. I think we can also argue that. So let's try to make this more formal, right? Okay, so you are right. So to make to apply for the stopping time, we have to just not worry about equality. We have to answer this question. Okay, so let's try to answer this. Okay, what we can do is, this correct? So I am saying that at any time t, m of t has to either less than or equals to n, or it has to be greater than or equals to n plus 1. This one of this must be true, and this should be equals to 1. Now I am going to write this bit n plus 1, and what is this going to be? 1 minus m of t is going to be greater than or equals to n plus 1, right? 1 minus of this, what is this is going to be? So this is going to be basically we have already said that if m of t has to be greater than or equals to n plus 1, in terms of z n plus 1, what we know, we know that this guy has to be z n plus 1 has to be less than or equals to t. We have argued that these two are the same events, right. So this both must be equal, okay. Okay, now let us see this. Z n plus 1 is nothing but summation of first n events, right. It is correct. I have just applied the definition of, let's say n plus 1 here. Now if I want to look at this 1 minus of this is basically 1 minus of this means the complement of this event, right. What is the complement of this event? The complement of this event, summation of I equals to 1 to n plus 1 xi is greater than or equals to t. Is this correct? Now the question that the question that is m of t is less than or equals to n has boiled down to asking the question whether the sum of the first n plus values has exceeded t, right. You see that. So what we want to know that n arrivals has happened in the within the interval 0 t, to ensure that I need to be confident that the nth plus 1 has not completely occurred within the interval 0 t, right. It must have ended after time t. So that is what exactly it is capturing. This is going to be the same as asking the question whether the first n plus 1 xi's their sum is going to exceed t, and so answering this question is equivalent to this, and to answer these questions how many xi's I need to know? N plus 1, right. So just knowing n random variables is not enough for me here. So you can also just like that think intuitively, right? Now that we have written this, if you want to know that within my interval 0 to t less than or equals to n might have happened and no more, that must be the case that n complete renewals must have been completed in that, and n plus 1th must not have been completed within the interval 0 to t. Had n plus 1th has also been completed in the interval 0 to t, then mt would have taken the value n plus 1, right. It would have been greater than n. So if m of t has to less than or equals to n, it must be the case that n plus 1th renewal might have completed in the after time t. So that is exactly it is capturing. So because of that, mt is not a stopping time. Now, so you somehow feel by this information that if I want to know that n arrivals or renewals has happened in the duration 0 to t, I need to know not n variables but actually n plus 1 renewal lives, right, or n plus 1 xi's. So it so turns out that m of t is not a stopping time, but if you just look at m of t plus 1 is a stopping time. Why is that? This is also actually obvious. So if I want to check whether m of t plus 1 is a stopping time, replace m of t by m of t plus 1, right. that is basically asking the question whether m of t is upper bounded by n minus 1. So in that case I have to replace n by n minus 1. So in this case it just summation happens to be I equals to 1 to only n. So in that case it only depends on the n random variables. But again this is the argument, but convince yourself that if I want to check whether mt plus 1 is a stopping time, that is the case.